Okay, so here's the video about specific heat capacity, the first part in the entire phase change. Okay, Miss, what is specific heat capacity?
Let us break down the term specific heat capacity first. So we know capacity is to take in energy. We know that when we heat up something, if you look at the heating curve, the something will happen to your temperature. Okay, so the ability for you to hold the heat in before changing state is kind of like the idea of capacity. But the term specific here is because we want to talk about a specific mass. Because of course you could say the amount of heat that a 1 kg block can store would be less than the amount of heat that a 10 kg block can store. So it's a unit mass. Like everything physics, we prefer our favorite number 1. So this will be the amount of heat required to increase the temperature of 1 kg of a substance by 1 degree Celsius. Okay. So if we actually write this out in an equation, the symbol here is C. So C would be equal to Q over M delta theta. Okay. Because the amount of heat required for 1 kg for 1 degree Celsius. And then we let M be equal to 1 kg and delta theta to be 1 degree Celsius. So let's say I have a 1 kg of this block of unknown metal and I put enough heat until the temperature increased by 1 degree Celsius. I measure that heat. That will be my specific heat capacity. Okay. So that's why if let's say we were to substitute 1, then your equation Q will be equal to C. Or C will
like that only, okay.
So it will just be equal. So that is why we define it that way. And if you intend to do more engineering and more physics, you have to get used to this kind of definition, not just memorize. But of course, we don't like fraction, so we rearrange to the more familiar Q is equal to MC delta theta. Unit for specific heat capacity would be joule per kilogram per degree Celsius. Okay, because the amount of heat, 1 kg by 1 degree Celsius, unit for C.
Miss, in Celsius not Kelvin Sometimes got Kelvin one, right?
But 1 Kelvin is 1 Celsius when it comes to temperature change.
Yes, okay.
So this one will be the unit for C. All right, so the first experimental setup that we will look at is the calorimeter. Okay, so this is a continuous flow calorimeter, or in chemistry we call this the Liebig condenser. So whenever there's an experiment, it's probably useful for you to think of the variables. So in this setup, right, what we will have is a tube where there's a heating coil inside the tube. Okay, and if you look at the heating coil, we are going to allow water to flow inside the coil and maintain the same temperature in and out of the heating coil. So water will go in from the bottom, flow and come up. Of course, you might be wondering why isn't the flow in the opposite direction? The short answer to that is if you reverse the water flow, you cannot fill the tube. If you understand your Liebig condenser in your chemistry, okay, that's why we fill from the bottom and then come up from the top. All right. So what we'll probably do is we'll plug a thermometer at both ends, okay, to measure the temperature of the liquid in and out. So in this experiment, what we will do is we will fix the amount of water flowing in the tube, okay, and then we heat up. Maybe we allow the heating coil to be there for a certain amount. So we're going to certain amount of time, but let's look at our variables first.
Okay.
So what are our independent variables here? We're going to heat this up. Let me draw the circuit as you write the variables.
Okay, so our variable, we're going to just let it pass through. So it's kind of like time, just let time flow and then we just watch what happens. So that's one thing that's happening here. Okay, so time is what we are choosing to change. Then dependent is what changes in response over time. So that will be the temperature that you measure, liquid in, liquid out. Okay, what's the temperature change? So let's write that there, temperature change, delta theta. Because now you have a, let me highlight for you. You go in 19.5, you come out as 25 now. There's a temperature change happening there. Lastly, constant variable. You cannot have too many things changing because too many things changing give you a headache. Yes. Is this changing? Is that changing? Is everything changing? Then how do I know my relationship between my independent and dependent is actually what it is? So here we're going to pump water in at a constant flow rate. So that'll be one of it. flow rate of water. What symbols shall we use? Mass per time lah. 1 second, how many kg, those kind of things. There is another one we should probably keep constant, and that is the heater power, electrical power.
And the way we keep it constant, if you observe the circuit that I've already drawn, is to have voltmeter and ammeter connected suitably, okay, in series and in parallel. And then you go and put a rheostat there and you adjust the rheostat to maintain the same IV reading. So ammeter is to read the current I, voltmeter is to read the potential difference V. Okay, so the temperature change delta theta would be T2 minus T1, the difference between the temperature in and temperature out. So if you go back to our previous equation, your Q is equal to MC delta theta. We will then substitute all our constants inside lah. Okay, so instead of giving you very abstract numbers, we will jump to an example. But before we do that, just would like to remind you, heat is power times time because heat is energy. And if you remember how to find power in the electrical circuit, we will use, what's the equation again?
PIV. I square R, V square R, I don't know. So
we use IV lah, because we got measure I and V here ma.
Okay lah. MC delta T. Okay.
So the second setup, before I move on to the example, I will not list down the variables because it's pretty, this one is actually simpler. What we do is instead of having the water flow in, flow out, it's just a standard calorimeter setup where I have an immersion heater, either a solid block or a water. And then sometimes I put a stirrer lah to stir. And this, then I just allow time to pass and measure the increase in temperature. The lagging and the shield is supposed to insulate your setup. Because when we do this kind of measurement now, we are assuming that there is no heat loss to the environment.
We try our best lah.
Yeah. We tap out this in some Uniqlo heat tech. So if you scroll a bit to the right, you will find some experimental setup that I found on the internet. This is the first one of the first calorimeters that is done. And then you can see it's almost identical to our drawing. Okay, this is from the 1940s. I found this in the museum.
It looks very ancient. Okay.
Museum archive. Okay, and heating coil is in the middle. So the more modern setup tend to look like this one. Okay, so you have an ammeter, you have a voltmeter. The calorimeter is actually the immersion heater, as you cannot tell, it's inside the Milo tin, and the thermometer is there, you can take the reading. Okay, sometimes we will use an AC voltage source, but you might be thinking, Miss, how do we calculate the power of an AC voltage? I'll do an example for you to see later. Then so when you open up the Milo tin, you can see inside that there's a stirrer, and there are some heating coils, one immersion heater, a bunch of immersion heater, doesn't matter. The blue color thing is what, Miss Ellie?
Looks like the insulation thing.
Yeah, so normally they will use something like a polyester,
polystyrene. Polyester is something else. I think actually polyester maybe can. I don't
organic chemistry.
I don't know. But yeah, something to prevent. Try the best. Emphasis on try to prevent heat loss
Yes, to the
surrounding.
So here we have some links if you want to go and click and see how the experiment is being done. But I think now we can jump to an example already. Okay, so we'll look at an example from page 15 of your handout, or Feb March 2016. Wow, first things first, 2 marks bonus for you. Define specific heat capacity.
Wow, throughout the whole thing. Okay.
Yes, amount of heat required.
Amount of heat required to do what?
To increase the temperature of a substance, to increase the temperature of 1 kg.
Miss, this one is 2 marks question. Where the 2 marks come from?
Of a substance by 1 degree Celsius. Amount of heat, the idea that you know specific heat capacity is actually heat or energy is 1 mark, and then the per unit mass per unit degree Celsius is the other mark. So the amount of heat required is 1 mark, and then 1 kg by 1 degree Celsius is the other mark. All right. Okay, B. Wow, so familiar, Miss, this one. You think I drew my own diagram, man? Of course, I cropped the diagram from past year paper lah.
This is exactly the one we looked at just now.
Yeah.
Okay.
So here, a student carries out an experiment to determine the specific capacity of a liquid using the apparatus. They don't even bother to draw the circuit for you. By the way, do you know why I draw a circuit or not? In case they ask you in paper 5. Miss, what is paper 5? You stay tuned.
Experiment, you have to design this whole experiment and
Yes,
talk about it.
hang on tightly, we will reach there. So liquid enters the tube at constant temperature, 19.5 degrees Celsius, and leaves the tube at 25.5 degrees Celsius. The mass of the liquid flowing through the tube per unit time is m. I would, if I'm a student now, I would underline this. Normally, mass per unit time, we use m over t, but now m over t is equal to m.
M. Wow, confusion, no.
Yes, I purposely
Wow.
confuse you. So you
So
better.
M equals to M over T.
Okay, maybe change in mass over t. Basically, you have to be careful in how you write your symbol so you don't get confused.
Mm-hmm.
Okay? Second thing to note here is that our variable seems a bit different because now the student changes m and adjusts p until the final temperature of the liquid leaving the tube is 25.5 degrees Celsius. Can we, Miss Ellie, identify the variables? Do you think that they are still the same?
I think it's different there because previously we keep power constant, we keep flow rate constant, but now your M and P is what is changing more.
And we measure the change in temperature, but now we keep the temperature constant, and then we change the other two things. Miss,
Such a troll, such a troll.
Don't know, maybe they've forgotten to bring their voltmeter and ammeter, so cannot measure.
Okay,
No.
constant.
Okay, so I'm gonna write beside the independent variable is this m and p. Then the constant variable would be temperature change. Okay, so data is shown below. You will find that when the power setting is different P, you will have a different flow rate. So whenever you get a table of data, before you very happily go and jump to something else, you have to ask yourself, am I understanding the question correctly or not? Which you can tell just based on this number. When the flow rate is smaller, 1.11 gram per second, this means in 1 second, you have about 1.11 gram of water flowing through.
Very little.
So if you want the amount, if you want to maintain the same temperature change, your heater cannot be so high. The power of the heater should be smaller. Does that make sense? And then if you are flowing more water into your setup and you still want to maintain the same temperature difference, you will then have to have a higher power setting. Okay, this is just for you to check. Okay, I am understanding the question correctly and I'm confident to continue. Suggest why the student obtains data for 2 rather than 1.
Why need 2, miss?
Take more reading and plot a suitable graph.
It's paper 3, miss.
Oh, sorry, wrong paper. This is paper 4.
Cannot say take more reading, plot a graph.
If you don't know, you skip lah. Don't know why. We do calculation first lah.
We'll come back to this one.
Calculate the specific capacity of the liquid.
You're like, oh, miss, I know. Just now we look at equation. The one Q equals to MC delta T.
Okay, correct. Only got one equation so far in this entire chapter. Well done.
But then we need to get to power, right? Okay, so energy is power times time, mass C delta data. Oh, then can plug in another equation, right?
Yes.
You got enough info?
But we have
the
the
mass
value of P.
Yeah, which one to use, miss? My confusion. You see this P? Which one should I take? I just choose the first one for now lah. Okay lah. What if I choose this? See what happens.
Okay.
Maybe can do later.
Maybe you choose the top one, I choose the bottom one.
Oh, do 2 Okay lah, we do both and see.
Answer lor,
Can.
So I'll write on top near my telephone number. So right now you can see Miss Ellie have already substituted the power. And the flow rate is an annoying 1.11 gram per second. And then you go and check the unit down here, kg. Hiya. So convert lor.
I cry.
Don't cry, just convert. Per
Delta
second.
T.
So per second means divide by 1 lah. So if you want, you can write over 1 so that it fits in your head. Don't want also can.
Never
We are
mind,
looking for C. And the delta T is
Oh, the temperature. Enter at 19.5, exit at 25.5. So I minus all.
No,
Can
means I
like
your
that.
question.
Can like that.
Because down here Kelvin
Oh, Miss, then I have to convert to Kelvin. I cannot
You
put
convert lah,
Celsius.
you convert and see what happens.
But then, Miss. Okay, never mind. We try and see lah. Huh?
Try
What
reply.
if I do? Okay, if I do 25.5 minus 19.5. You should remember from the previous example video lah. Okay, if this is in Celsius, this will be the same amount. Delta C, which is also the same thing as if you put it in Kelvin and then you minus, you still have the
Because
same.
on this side, you're going to put 273.2, remember? 0.15.2. And then up here, you're going to have another 273.2. So you will see that you will minus away the same amount, which is the same thing. Does that
actually doesn't matter lah.
Yeah, it doesn't matter.
You can shortcut a bit.
Yes. So the change in temperature, with change in temperature, you don't have to convert. Absolute temperature, then you have to. Okay? Right. But if you're not sure, then you convert law, and then you notice that your conversion cancels out, and then you feel a bit dumb lah, but it's fine.
Okay, what's the C value? No calculator again.
5,000. And the other one is...
There's a small difference there. Is that negligible? Then which answer should I take?
I don't think it's negligible.
So why is there a difference, Miss? You take first reading, got a problem. You take second reading, they don't agree. How? GG liao lor.
I think there is this thing called surrounding.
Surrounding? What do you mean surrounding? Let's look at this thing again closely. What do you mean by surrounding?
You see, the heater heat the water, but then will it accidentally also heat the environment?
I think it does actually, because if your water is hot, some heat will just escape.
Yes. Miss, I don't know what is the heat loss to the surrounding.
So how do you calculate the heat loss to surrounding? We want to account for that. Don't know how.
Wait, is that the answer for part A?
Huh?
Maybe that's why they gave us 2 readings. Let's go back to
here.
Go back to A, no B or whatever. Why the student obtain data for 2 value of M rather than for 1 value? So it's to account for the heat loss to surrounding.
Then the next question is, Miss, how?
How? We need to modify our calculation in part 2. So we need to think a bit using conservation of energy. The power give the system heat, but not all of that heat went to increasing the temperature. So not all the heat went to MC delta theta. So your PT will be MC delta theta plus what is lost to the surrounding. So can change maybe a different color.
Use red color.
Can. So it will be MC delta theta plus heat loss to surrounding.
Oops, P. Where's my T? So coming in is power from heater. Then some energy go to the water liquid. But then also...
I think this one we put Q loss lah. Can
Q loss can.
Or QL.
So you use both value, you will have a QL.
Because of me, so I notice if I continue here, I can keep my calculation now, right? The working can keep. What I need to do is I just need to add a QL at the back, correct? Of my calculation. Yes.
Yes, this one wrong now.
So now the thing is we got 2 unknown. 1 equation can solve or not?
Can. Got this thing simultaneous equation, I think.
Yes, because we got 2 readings, so we can simul. So if let's say you accidentally forgotten to do this, you don't have to rub off your entire working and cry in the corner. You just write the heat loss at the side of your calculation. Okay.
So we can sub out the heat loss lah. You're very long to rewrite. Okay lah, right.
Generally, if you are not very good in maths, I would suggest that you use a pencil to circle your variables or your unknown, especially when the numbers are all over the place like this.
Or you cannot bring highlighter lah, so you cannot highlight like this.
Cambridge like to micro what you bring in the lab in your exam. So I'm going to take. So we do not need to find QL. So I have to eliminate QL. And the easiest way to eliminate QL is to take equation 2 minus equation 1. right? So I will write here
Yes.
2 minus 1. Miss Ellie, I'm writing, but it's not appearing. I am sadness.
I write lah. 2
Okay.
minus 1.
I already label with 1 and 2.
I
So
label
write
again lah.
equation 2 minus equation 1. Okay. And you will see that on one side, you will have 44.9 minus 33.3. And then the other side,
All the stuff.
okay, so you minus these two. Okay.
Minus lah. Just minus like that.
Yes, can. So when you minus, you have to be careful. One side is 44.9 minus 33.3. Okay, and then you mean you want to press now?
Can press now also lah.
Okay, I suggest, right, for marking and writing your working during exam, to actually show this part, because this part got marks if you check the marking scheme. That's why they say show your working. Okay. So write out this one, 44.9 minus 33.3. Whether you transfer like what Miss Ellie did or not, it's up to you whether you need it, but you should.
Many ways to solve it lah. Just make sure you write working lah.
Okay, so the next part is C. So when we write C, right, what we will do is, the first thing I'll do is I'll find the temperature difference.
Yes.
Which is 6 degrees. Okay. And then so I will multiply by 1.58. So this will be 9.48 minus 6.66 C, can, or big bracket.
Yes, easier.
Times 10 to the power of negative 3. Okay, and the QL and QL disappear.
QL is gone already. QL minus QL is just nothing.
So now you have this one divided by, so now you can just easily press your calculator, provided your units are converted.
Press calculator.
4110. This makes more sense.
Magic. So it's neither of the reading. It's somewhere, something even lower.
Because, and you know why it's lower? So the previous reading, right, if we recall just now, I will write, or
I think it was 5,000 and 4,700. That was our values lah.
Okay, so this is an overestimation, but let me draw back first to the 4110. If you do enough past year question, or if you have done this before in your SPM or your IG, you will remember that the specific heat capacity of water is around 4001 or 4002. So you should get around that number. If you get something very weird like 5,000, that is a bit too big already. Yeah.
Overestimate now.
So these two are overestimation. So when we say overestimation, it means that you need more heat than you initially thought you needed. Okay, so let's say, for example, I want to increase 1 kg water by 1 degree Celsius. I need 410 joule. Actually, I need 410. But unfortunately, because the environment stole away some of my heat, it feels like I need more.
Because you have to keep putting in, ma.
Yeah.
But it's lost, it's lost, it's lost.
So this is an overestimate. So if we go back to our notes,
let's add this idea here. If not, next time, sure, forget one during exam, do halfway. Eh? Why all wrong, miss? All my past year. Do you estimate? You take into account the heat? Okay, let's write that down here.
So generally, you just put a subscript heater lah, okay, plus heat loss to environment. And this one, if let's say you didn't account for heat loss, your calculator answer will be an overestimate. This is also a common past year question. Sometimes they only give you one reading, so you totally cannot count heat loss one. And then they ask you, is your answer an overestimate or underestimate of the theoretical answer? Okay, so if you don't account for heat loss, like the way we did in this calculation, in our previous calculation, then whatever answer you got, 5,000, 4,007, is an overestimate. You thought you need more, but actually you don't need that much. Okay. Do not forget, hashtag reality. Miss Ellie wrote so many notes already. If you still forget, then I don't know. Okay, let's move on to the last part of the question.
Okay, wait. I must write more heat use. Okay.
More things, or more rate, not the exclamation point.
Put all the exclamation point everywhere. Wow, why got a sign here? Okay.
Okay, so the heating coil dissipates 33.3 watt of power. The potential difference is given by this expression. So whenever you see this kind of sign expression, Miss Ellie, can we sketch out a sign graph?
Sure, let's go.
Okay, so this is the potential difference. Got positive, got negative, meaning we keep changing the polarity of our power supply. This is alternating current.
Means this is not battery anymore.
Chapter 24. Miss A2 got how many chapter? I'm only in chapter 11. I don't know. We see how lah. So chapter 24. Okay, so this chapter 24, if you see this sine graph, if you know a bit about properties of sine graph, the amplitude is 27 lah. Okay, determine the resistance of the coil. Okay, so there's one thing about alternating current that you may or may not know, which is the root mean square values. Now, when we enter chapter 24, I will derive, or we will derive, the root mean square equation for you. But if you don't know, now you just have to use first. And if you did SPM, we have already shown the equation to you before. VRMS is maximum Vmax over root 2. Or the peak
strange equation
over root 2. We explain later. We got some sine cosine thing to differentiate one. Okay. So what the maximum value here is 27. So it will be 27 over root 2. So this root mean square, the idea of root mean square is we are trying to find a way to find the average for this graph. But the problem with this graph is if we take the absolute average, you're going to get 0.
Because your positive got negative, your average becomes 0.
Alright, okay. And no current, man, GG. So actually got current one. And the resistor don't care the direction of the current. The resistor just say, you go give me current, I will heat up. I'm a simple resistor. Got current, I heat up. So what we'll do is we'll square everything, like how you do standard deviations, okay? And then we square root again. So the root mean square here, you can treat this as some form of average value. Square already, then average. Like how you find standard deviation. Real stats. It's a method we do when our data got plus and minus.
Yeah, so if you're wondering how it's square, like all the positive, all the negative become positive, so it's something like that.
So this one, this 19.1 is a representative of the potential difference across the heater. So then we can use the equation. Average power, P min, will be equal to VRMS square over R.
V square over R is a good old thing. Okay, you're a good old friend.
So if you think you can forget everything from your AS, I guess you know now it's not true lah.
Cannot, must keep in your brain.
Yes. So you're looking for R. Do we have the average power? Oh, there? 33.3.
They told us.
I press for you.
You press for me. I write
I press
R.
for you.
So the R will be?
Your R is 10.96 ohm. You write 2, 3 SF law, so maybe 11.
11 lah, 11 nicer.
11.
3 marks, where the 3 marks come from, or miss?
Okay, so let us rewind back. Rewind, and we allocate all the marks. So for A, thermal energy required, sorry, the marks give me to adjust a bit. Thermal energy required for 1 kg is 1 mark. Raise the temperature of 1 kg is 1 mark. 1 degree Celsius is 1 mark.
3.
The amount of heat required to raise the temperature of 1 kg is 1 mark. Then the 1 degree Celsius is the second mark.
Wow, 1 degree Celsius also got 1 mark. Okay.
1 kg.
1 kg.
All right. And then
this one suggests why the student obtain data.
To allow or to determine heat transfer to surrounding. Okay, correct, to account for heat loss to surrounding. Do not allow to prevent heat loss from surrounding.
Cannot. How are you going to prevent? Cannot. You take more data, then the less heat loss, man.
The amount. Okay, so this one is 3 marks. The first mark is when you write PT is equal to MC delta theta plus heat loss to surrounding. Okay. I would also like to mention that since they represent M as M over T, it would be a bit better if you change this M, the small m, to maybe big M or something like that.
Some other alphabet lah.
Other alphabet because they annoyingly
They go and choose M as the
mess over time.
okay.
Okay. So then you substitute with one values, either you arrive to equation 1 or equation 2.
Also
Together with writing out this equation is 1 mark. So this two thing is only 1 mark.
Okay.
You showing the subtraction 44.9 minus 33.3 line, this line is 1 mark. The final answer is 1 mark.
4, miss.
Yes. And in fact, they very specifically said that it should be 44.9 minus 33.3 is equal to, so you need to see this one, this whole thing.
Must show, must show.
Must show, yes. Okay. This 3 mark is easier to get. If you know that your Vmax is 27, you get 1 mark. If you find your VRMS, you get 2nd mark. And then you use the power equation leading to 11, you get the next mark. Okay.
Okay.
So,
it's a new thing, miss.
Which one?
More. This alternating current one.
Yeah lah. So right now, if you, because in different subtopics leading to chapter 24, alternating current makes a guest appearance. And the reason to that is because alternating current is a very short chapter. And they are seldom asked as a standalone. So they like to put it all over the place to test you. And so that's why you see it everywhere lah. So I would, if it's here, I don't think we should avoid the question. So it's a straightforward enough understanding where if you want to find the average of a sine graph, we do
square
this,
everything, average, 2 steps.
And square root. That's why we call the root mean square. And guess what? We will do root mean square in the ideal guess chapter again.
It will come back.
Come back. This idea of root mean square.
Okay, so that's the end of this in-depth, very tricky, very strange past year example. Next one, we're going to look at the next part of the story lah,
So
next one will be here. What happens here?
Oh, yes. What happens during state change? So right now, what we are doing is just, let's say, for example, you look at the part where the temperature increases. Okay, so these are all, here we can calculate our C. All right. So all this part where there's a gradient, we can calculate our C. So like, for example, the first C starting from the left, that would be the C for your solid. They might not be the same C.
That's true. Liquid
for ice and specific heat capacity for water and specific heat capacity for gas is not the same.
Slightly different.
In fact, it's very different. It's harder to heat gas. Remember, gas is a very good insulator. The particle far apart, very hard to pass vibration.
Cannot
vibrate someone far away. Come vibrate with me.
Cannot.
Okay. So we use this to calculate C's. You please do more past year questions. And unfortunately, because there are no objectives, all questions will be long from now on. Welcome to A2. And I will see you in the next video where we'll talk about the very last thing, state change and latent heats. Bye-bye.